This is our project VoicePD for this hackathon. The main goal of this project is to enable early detection of Parkinson's disease through vocal biomarkers and machine learning. This project was created by Kevin Chow and
Aaron Kim. Introduction. Over 15.6% of females and 18.1% of males develop Parkinson's when over 80. Parkinson's can lead to early retirement, high medical cost, and lowering life quality. Parkinson's early detect is hard as visible symptoms typically appear only after when 60 to 70% of the neurons are damaged. Our goal is to enable people to detect Parkinson's disease in an early stage easily via vocal biomarkers so they can save money, time, and maintain a better quality of life. What's Parkinson's disease? Parkinson's is the second most common neurodegenerative disease after Alzheimer's. The most visible features of this disease are slow movement, muscle rigidity, and resting tremors.
some non-motor features are voice changes, depression, cognitive deficits, sleep disturbances, loss of smell, bladder dysfunction, gastrointestinal problems, cardiovascular dysfunction.
Parkinson's can affect various types of neurons. However, most focus has been placed on the neurons in the brain, notably origin of the midbrain called the substantia nigra. Substantia nigra forms a part of a major pathway in the brain that's critical for precise control of muscles. In Parkinson's, the dopaminergic neurons gradually die, leading to the dysfunction of this pathway. Connections with patient's voice. In Parkinson's, the loss of dopaminergic neurons leading to difficulties in controlling throat muscles, including lingual and tongue. These changes lead to a subtle alteration in the patient's voice, which can be detected using AI and enabling better symptoms management and early therapeutic interventions. Our accuracy was 85%, tested with 3,000 spectrograms, and it was trained with 15,000 spectrograms.
As you can see on the right side, this is our final log from our training block of code. We trained via 5-fold and per-fold accuracies are listed above. The mean accuracy, basically the overall, was 85%. So, data. Our model was trained on the public dataset Empower provided by Synapse, which you can see on the right. And the dataset was comprised of many unique individuals with different ages and genders. And to minimize demographic bias, we implemented age and gender matching, which selected individuals based on the same age and plus or minus 2 years to pair Parkinson's patients with healthy patients. And due to computational limits, we scaled down our dataset from 40,000 plus, which was the original size of the Empower dataset, to 15,000, and ensured a 50-50 split of Parkinson's patients with healthy patients. So that was 7,500 Parkinson's patients data and 7,500 healthy patient data. And the dataset was originally comprised of raw audio files, and we converted them into MEL spectrograms. Now, data preparation and augmentation. The inputs were MEL spectrograms and their corresponding binary labels. For pre-processing, we handled NAND values and applied Z-score standardization to each spectrogram. Now, augmentations are basically used to make the data more robust and prevent overfitting. We mainly use 4 types of augmentation: spec augment, which randomly masks out blocks of frequencies and time steps. Additive noise adds Gaussian noise to spectrograms. Time shift randomly shifts spectrograms horizontally. Mix-up blends two spectrograms and their labels. Here's an example of spec augment, where you can see this is missing and this is missing. And mix-up, where you can see that these spectrograms are combined. Now, model architecture. So, we used an efficient net plus LSTM. The backbone was a pre-trained efficient net. The specific model was the efficient net B0, and we used it for powerful feature extraction from the spectrograms. We modified the efficient net to accept single channel spectrograms and remove the original classification head and added a custom classification head we'll talk about later. And for the bidirectional LSTM, which is long short-term memory, it basically captures long-term patterns in the spectrogram, and we added an attention mechanism to focus on the most relevant part of the spectrogram, and we added a custom classification head, similar to the pre-trained efficient net, and it's a stack of dense layers with batch normalization, relay activation, and dropout. And the head returns out, and the head outputs probabilities for two classes. And now hyperparameter optimization using Optuna. Manual hyperparameter optimization is usually super tedious, so we decided to use Optuna to automatically find the best combination of hyperparameters for optimal model performance. And the parameters we tune are here: learning rate, batch size, dropout, weight decay, noise standardization, frequency mass parameter, time mass parameter, and mix-up alpha. And training strategy. So for our loss function, we used the cross entropy loss. For optimizer, we used MW. For learning rate scheduler, we used the cosine and leading learning rate. And we employed a two-stage fine-tuning process. Stage 1 was initial training. So it trains the model's head and the recurrent layers while the efficient net backbone is partially frozen, allowing the model to adapt to a new task without drastically altering or changing the efficient net's pre-trained features. And stage 2, which was fine-tuning. So after initial training, the entire efficient net backbone is unfrozen and the model is further trained with a much lower learning rate, which allows for fine-tuning all layers to a specific dataset. And for cross-validation, we used a 5-fold version of the stratified k-fold cross-validation, and we employed early stopping. And summary, our project basically helps people to get early treatment by detecting Parkinson's disease earlier on any device, which can save a lot of money and possibly lives. By simply just saying for 7 seconds, the program will return how confident it is that you have Parkinson's disease. And here's our sources. Thank you.